Everyone, looking at class number 30. This is a class where we focus on Newton's third law. We've mentioned it before. It's, basically the idea is a reaction has an equal and opposite reaction. We'll go through the exact definition in just a bit, but just keep it in your mind. That's what Newton's third law is. So there were a couple of videos to watch from the movie The Martian. I would totally recommend, well, one, watching the movie, reading the book, but also make sure you watch those videos before you go on. So the first thing says, how can Newton's third law be used to explain Watney's plan for traveling through, that should be through space, not through space. In the scene, what you noticed was Mark Watney said, all right, I am going to poke a hole in my spacesuit and air is going to escape from my suit. And I can use that air escaping from my suit as a thruster to push me forward through space. Now, the reason this works, this actually works. This is how they correct satellites' orbits, International Space Station's orbits. You actually also see it in another spot in the scene where the person who's catching him has little jets kind of firing off so she can move all different directions. This is a great application of Newton's third law. Basically, what's happening is his suit is, quote unquote, I put in quotes here, pushing air out. By doing that, the air has to push his suit the other way. So if he, let's say, takes his hand with the hole in it, with the suit with the hole in it, and he points it forward, let's say, the air is going to be pushed forward. Therefore, the air is going to push him backward. Right? That's Newton's third law. It has to work like that. It can't happen any other way. The air can't escape from his suit going one way without pushing him back the other way. That's also a great example of the conservation of momentum, which we'll get to in the near future. Now, the next part is a little bit. It says Newton's first law, or use Newton's law while Watney keeps floating past his original target. An object in motion will stay in motion in a straight line at constant velocity unless acted upon by a net force. So what happens is, he fires off, he's going towards his target, and once he gets to his target, the person who's trying to catch him, he can't stop, right? Because he kind of forgot maybe that, well, Newton's first law tells me that I'm not going to be able to stop unless there's a net force acting on me. And the person that tried to grab him couldn't apply enough force to stop him, and I guess he didn't really have enough control with his suit to see, to change direction quick enough or to stop quick enough. All right. So number 4 is a great example of Newton's third law in action. It says, take a look at the image to the right. What propels the runner forward? So a lot of people might say, oh, the runner's legs pushing off the ground. That's not exactly what pushes the runner forward. You'll see in picture A, it says the runner pushes back and down on the ground. So the runner, this happens when you walk. The runner pushes down and back on the floor. According to Newton's third law, the ground pushes forward and up on the runner. So what's sending the runner forward is actually the ground, okay? It's not necessarily the runner moving his legs, though his legs moving create a force on the ground, which in turn creates a force back on him. So yeah, it is him. But think about it this way. Think about why Mark Watney in the video we watched, why couldn't he just walk through space? Why couldn't he just move his legs and walk through space? Sounds like a silly question. Well, there's no ground for him to push off of and to push back on him. So as much as if he wanted to flutter his legs back and forth, he'd go nowhere. Okay, because there's no ground to push back on him to move him across space. So here's Newton's third law. All forces come in pairs, and the forces are equal in strength, opposite in direction, and act on different objects. That's really important. They act on different objects. A lot of people, they see, let's say they have an object sitting on Earth's surface, and there's weight pulling down on it and normal force pushing up on it. That is actually not of Newton's third law, because those are not action-reaction pairs. They are not forces acting on different objects, okay? Now we kind of get into action-reaction pairs here, but then, I started to realize it is definitely a bit of a confusing topic for something that doesn't have to be, we don't really have to cover. So I decided not to really go into it here with some of my classes. I think one of my classes we did, but the rest I said, you know what, just forget it. We're not going to go over this. So if you're interested in what the answers are to this or what it should look like, I'll be happy to talk about it with you. Now, the next question says, you are walking along and slip on some ice and fall. For a moment, you are in free fall. So say you slip, your feet go way up in the air, and for a moment, you're in free fall. During this time, what force do you exert on the Earth if your mass is 55 kilograms? Draw a free body diagram on you and draw one for Earth. I have one for you, but think about it. So it's how much force you exert on the Earth. Well, that should be equal to the amount of force that the Earth exerts on you, right? According to Newton's third law. So the force that the Earth exerts on you, that's the force of gravity. So in this case, the force of gravity acting on you is 539 newtons pointing down. Therefore, you have to apply a force of 539 newtons upward on the Earth. Now, you might not think about it like this, but this is true. Right now, as I sit here, a force of, let's say, 1,000 newtons acts on me, pulling me down. That's the Earth pulling me down. I am actually pulling up on the Earth with 1,000 newtons as well, okay, in equal and opposite force. You might not notice it because the mass of the Earth is so gigantic compared to the small force, relatively small force. So that's why you don't really notice it. But this happens same with the Earth and the Sun. The gravity, the force of gravity from the Sun pulls the Earth and holds it in its orbit. The Earth also pulls on the Sun. Now, the Sun is so massive that if you think of A equals F net over M is so big that the acceleration, the change in velocity of the Sun due to the Earth is negligible. All right, we'll talk more about that when we get into orbits. Now, numbers 12, 13, and 14 are as hard as you will find on a Regents exam when it comes to Newton's third law. So let's check them out. The first one says a 40-kilogram child exerts a 100 Newton force on a 50-kilogram object. The magnitude of the force that the child exerts, that the object exerts on the child is, so if the child exerts 100 Newton force on the object exerts 100 newtons back on the child. The reason they put these masses in here is because they're hoping you'll like get confused and put down the weight of the child or the weight of the object. No, the child pushes with 100 newtons, it pushes back with 100 newtons. Now you might be saying, why isn't it negative? Doesn't it point the other way? Well, it's asking for the magnitude of the force, so that doesn't really care positive, negative, it just wants the size of the number. Number 13 says, as a hammer hits a nail into a piece of wood, which is greater, the force of the hammer on the nail or the force of the nail on the hammer? So that you take a hammer, you hit a nail. Which one exerts more force on which? Now, we know this, we've spoken about this before. If I punch a wall with a force of 500 newtons, the reason my hand breaks is because that wall is punching me back effectively with 500 newtons. Okay, so it doesn't matter which is hitting which, those forces are going to be equal. And the last one, a tennis player's racket applies an average force of 200 newtons to a tennis ball for 0.025 seconds. The average force exerted on the racket by the tennis ball is going to be the opposite of that, 200 newtons. So if a racket exerts 200 newtons on a tennis ball, the tennis ball exerts 200 newtons back on the racket. That's why if you hit a ball hard, like really, really hard, you could damage the racket. Let's say you hit a ball that's not a tennis ball, the tennis racket, you could break the racket. Because yeah, you might be hitting that ball really hard, but the ball's hitting your racket just as hard. All right. So that's everything you really need to know for Newton's three laws. If you're good with 12, 13, and 14, for Newton's third law. If you're good with 12, 13, and 14, you are good for Newton's third law. All right. Have a great day, everybody.